Hello everybody. In this topic we study new concept, circuit theorem. In the past few chapter we have studied Ohm's law, circuit, Kirchhoff current law, Kirchhoff voltage law, then also branch current analysis, mesh current analysis, nodal voltage analysis. Now we proceed to more advanced theorem. All this in this chapter we will still focus on what? We still focus on DC, direct current. The theorem we're going to study is what? First, superposition theorem. Next is Thevenin theorem, Norton theorem, Milman theorem, syllabus, maximum power transfer theorem, and conversion and star delta conversion. First, superposition theorem. Superposition theorem states that there is in a linear circuit or network containing several voltage and or current source. Can several voltage or current source? The current through or the voltage across any element is equal to the algebra sum of current and voltage. So, for current source, for voltage source, after considering we take out, we replace with a short circuit. For current source, we replace it with an open circuit. This means that a superposition theorem is a theorem that used in a circuit that contains two or more source, no matter it's current source or voltage source. For example, in example 4.1 state that using the superposition theorem determine current I2, determine this current I2 through 12 ohm through this 12 ohm resistor. So first we need to consider 45 volt only. Then for this voltage source 48 ohm, we sort it like this. Voltage source we sort it like this. So we sort this one, consider E1. So we get this part. Okay, this part. Next, we consider 48 volt and sorted 45 volt according to here. Then we get this circuit. For these two circuits, we find the component due to I2. For the component due to 54 volt is I4. The component in R2 due to 48 volt is I3. Then we find separately I4 and I3 we find separately. Then after that we superimpose it to get the final value for I2. How to find? First, from the circuit of 4.2, after applying superposition, we get circuit of this one A and B after applying superposition. So this part is what? This part is parallel. So parallel is R2 and R3 parallel. Then we find this total resistance is R1 plus R2 parallel R3. Then to find this IS is what? 54 divided by R total. R total means that whole R here. So this one parallel is 3 ohm. So IS is equal to 2 ampere. Then after getting IS, we use current divider law to find I4. Is what? Is 4 divided by 12 plus 4 times what? 2. equal to 0.5. Then 4.3b, this is for this one, this part is for this part is for 54 volt. Next, for circuit B is 48 volt. We repeat the same thing. This one is parallel. It's parallel. It's R1 parallel R2 plus. This one is R3. Then we get R total. It's R1 parallel R2 plus R3. So voltage 48. Voltage source 48. 48 divided by this R total equal to 4 ampere. So this one is, here is 4 ampere. For this part, current 2 here is what? 4 ampere. Then we can divide the rule, divide the law. I3 is what? Opposite one, 24 divided by 12 plus 24 times what? 4 equal to 2.66. 2.66 is I3. Next, superposition is what? I2, 42 here is I2. I2 is 42 12 ohm. For due to this 54 and 48 watt simultaneously is what? Is I4 add with minus I3 is minus I4 minus I3 is 0.5 minus 2.66 is minus 2.1166. Then this one is for the superposition theorem to find current for due to two source. Now this one, next example is superposition. Use superposition to find voltage at point P due to two voltage, due to two voltage 24 and 9 minus 9. Okay. Next, we do Thevenin theorem. Any two-terminal network containing resistance and voltage and or current source can be replaced by an equivalent circuit consisting of a single voltage source in series with a single resistance. Any two-terminal network, it contains resistance and also voltage or current source. It can be replaced by an equivalent circuit consisting of only a single voltage source in series with a single resistance. Means that for this circuit, use Thevenin theorem to find the voltage across and current through RL. So current and voltage and cross and current through RL. So we need to simplify this part to a single voltage source series with a series resistance. Means that we want to find this RL voltage and cos RL and current through RL. We take this one, take this one, remove this one apart, then we form this one. Remove this apart, form this one. Then from this one, we find VTH. Find VTH. VTH is what? From this is voltage across R2, 6 ohm. So we use voltage divider rule. Is 6 divided by 6 plus 3 times 36. 6 divided by 9 times 36 is 24. So VTH is 24. Then RTH. Look at here also. RTH look at here also. Take this voltage source out, short it as done. Voltage source take out and short it. So we got these two, short it in red. So we short it. So we got these two parallel. These two are parallel. Parallel is 3 parallel 6 is what? 3 parallel 6 is 2 ohm. So we have reduced this complex circuit in here, in this part, to a single voltage source series with a series resistance, which are 24 volt, VTH 24, RTH 2 ohm. Then after that, After form this one, this circuit, we just now we remove this one. Now we join back to here, equivalent to we join back to here 2 ohm. RTH 2 ohm, R load also 2 ohm. R load 2 ohm. This is not necessarily the same, man. They are RTH and IR not necessarily the same. So to find load current IL is VTH 24 divided by 2 plus 2, 6 ampere. That 6 ampere per to here, voltage will be 6 times 2, 12. Okay. So this one is Thevenin voltage due to single source. Thevenin voltage for more complex circuit with a resistor and more source, like this case. One is current source, one is voltage source. Can be more than that also. Just a previous example, only single source. Now this got 2 source. So we do what? We want to find, use Thevenin theorem to find current through 22 ohm. 22 ohm. So what we do? First, current to 22 ohm, this part. So do first. So first we take this one out. Current to 22 ohm, we take 22 ohm out. Take 22 ohm out, we left with what? We left with this part. Left with this part is actually this part. Actually this part. Then this part we find VTH. We find VTH and RTH. Thevenin voltage and Thevenin resistance of this part. Reduce VTH and RTH, then reduce this part to a single voltage source, single resistance, series resistance, and then join back the R422 and then find the what? Current. Okay, this Thevenin voltage, Thevenin theorem. Then how to find this one? VTH. Then this one VTH, we got 2 source. To find VTH, we may use what? Superposition theorem. Then first, we consider voltage source first. Then we open current source, we open it. This one open. So the VTH voltage will be what? This point to this point is R1 plus R2 divided by R1 plus R2 plus 3 plus R3 times what? This part is minus. Top negative part point up, so it's minus 12. So it's 5 divided by 8. So it's minus 7.5. Then next, short this one. Remain this one. Short this one. Consider current source, then voltage source we short it. Then the current flow to R3. To find current flow, to find the current to R3, this shorted. We flow to here. This branch spilled 2 branch. Current flow to here spilled. Current divider log. Current flow to here spilled these 2 branch. Then this one current flow to R3 is what? 4 opposite 4 ohm. 4 ohm divided by 4 plus 1 plus 3 divided by times 8 equals to 4 ampere. This current 4 ampere. 4 times 3, 12 volt. It's 12 volt. So VTH will be 12 plus 7.5. 12 plus negative 7.5 is 4.5. Then for resistance, for Thevenin resistance, this one shorted, this one open. So you get this circuit. So this one and this one parallel is 3 parallel 5. 3 parallel 5 equal to 1.87 ohm. So this one is Thevenin voltage, Thevenin equivalent circuit for this part. We want to find what current to the of there. After simplify this to single voltage source and series resistance, we connect this 22 ohm back. Then we find the current is what? Easy. Just simple with total voltage 4.5 divided by total resistance 1.875 plus 22. So it's 188.5 milliampere. Okay. So this example 4.5 we will explain during full lecture. Next, Norton theorem. Norton theorem is what? Previously, Thevenin theorem is reduce the complex circuit to a single voltage source with a series resistance. Okay, single voltage source and series resistance. Now, if we use the same technique, we reduce to what? To a reduce the circuit to a what? To a single current source with a parallel resistance. Then this will be called a what? This will be called Norton theorem. Norton theorem. We reduce the complex circuit to a single current source in parallel with a resistance. So take example. This example. This is the previous example. In this example, now we use Norton theorem to find voltage across RL and current through RL. This one we are done using Thevenin in this example. We use using Thevenin in this example. We use Thevenin in this example. We use Thevenin in this example. Find current through RL. We use Norton, we will get the same answer. We try to see whether we can get this answer, these two answers, not 6 and 12. Use Norton, use Norton theorem. First, current Norton will take this one out. Norton theorem will take this one out. We find a current, so we need to take out. We short it. But then label is flow in this direction IS. So current will come to here. Get two choices. One is 6 ohm, one is 0 ohm. So all current will come to here and then should all flow through here. So this IS is 36 divided by 3 is 12. 36 divided by 3 is 12 ampere. Then this voltage source solid. Then look at RS. It's 3 parallel 6 is 2 ohm. So we reduce current pointed down, so it's point upward. Pointed down, so it is a flow in this direction. So if positive is pointed outward. Pointed outward is 12 ampere parallel with 2 ohm. Then this join back RL. Join back the RL. We join back RL here. Join back this RL. Join back this RL. We join back. So we use current divider rule to find IL. This is Norton circuit. IL is 2 divided by 2 plus 2 opposite branch times 12 is 6. So it's 6 ampere. Voltage is 6 plus 2, 12. It's 6 ampere. 12 volt is same. Same as here. Same as this one. 6 ampere and 12 volt using Thevenin theorem. Thevenin theorem and Norton theorem will ultimately arrive at the same answer, correct answer, same correct answer. Only their method is different. Then Thevenin Norton conversion. Thevenin equivalent circuit is a voltage source, some sort of like voltage source. It can convert to Norton equivalent. Thevenin equivalent circuit using source conversion, same as normal source conversion. Then Millman theorem is not inside syllabus anymore. Next, maximum power transfer theorem. Maximum power transfer theorem. Let's say we want maximum power transfer theorem state that a load will receive maximum power from a network when its resistance is exactly equal to Thevenin resistance of the network applied to the load. Let's say we have one load. We have one load RL. One load, like the bulb, light bulb. Then we have one supply, one circuit, one network. If we want to find what type of maximum power that the light can be the more light will supply to the light bulb, we will want to find the resistance. So we need to find the whole network, this network. We reduce the whole complete network to a voltage Thevenin equivalent circuit with the VTH then RTH, whole complex VTH, whole network we reduce it to a single Thevenin voltage and series resistance. Then we join back the load. Then if we adjust the load resistance to equal to the Thevenin resistance, then if same, it will get maximum what? Power. The load or the light bulb will get the maximum power. The maximum power formula is what? VTH divided by 4 RTH. VTH square divided by 4 RTH. This is maximum power theorem. VTH square divided by 4 RTH. See now? The curve is, if we plot load power 100%, percentage 100%, it get 100% over 100%. Load reduce from 0 to 30. Any load, it reach what? It reach 100% when RL equal to RTH. Okay? RL or so for circuit in 4.23, let's say 4.23 here. If we fix this one RTH at what? RTH at what? At 9. If we fix RTH to be 9 ohm, power dissipate to the load PL versus load resistance is plotted. Then we plot the power to here. Again what? Again this RL change value. This one fixed at 9. This one we measure the power. Again the variation of RL change from 0 to 30. So the power will get maximum when this RL become equal to this one. This one 9. So this one will be equal to 9. Then it will be maximum. Remember, we change the 0 to 30. So you see, we get the power 100% when it's 0 to 30. We plot the power. The power we plot until the maximum is when RL equal to RTH 9 ohm. Then after that it slope down. Okay? This is maximum, typical maximum power transfer curve. Next, we study star delta connections. This one is called T. This one is called T. T or called Y. T connection. We got T connection or Y connection. This T connection or Y or called star connection. These two. These are the same. Next one is another called what? Pi. This pi or delta. Pi connection or delta connection. This one the same. These three connections, why needs to study this connection? Because when you study like this circuit, you want to measure ITH, total current through the circuit, total whole current through the circuit. How to get the what? To find IT, we need to get what? Whole resistance, total resistance of this one, total resistance of this part, this network. So, but we cannot get series parallel nicely. We cannot use normal series and parallel theorem connection to do the equivalent circuit. So we need to do what? We need to convert this part, this delta, convert this delta to Y. See that? Convert to delta to Y using this relation. Using this relation. You think delta to Y network, delta network to Y network. Equation 4.7. Then we reduce this one from here, from this part. We reduce this one, to P1, P2 to this part. So after doing what, we can do what? These two series, then here and here are parallel, then find these two parallel, then we can find the whole thing, the result, then can find IT. Okay? Next, we will do the full lecture when we have full lecture when we start with our lecture class on this topic. Thanks for listening.